Hi everybody, it's Mr. Tublizo from the Algebra team again, and today's topic is going to be about functions. And if you recall from Mr. Gallatin's presentations, there are two kinds of functions, right? One that has the dots connected, right? That's because there's an infinite number of points right here. Right? And it's hard to just draw dots for each one of those because they're infinite. And so what we do is we connect them with a line or a curve, and we call those functions continuous. Okay? And then there's those other kinds of functions called discrete functions. And the reason they're called discrete is because there are only certain points. In this particular case, there are only 5 points in this discrete graph. Okay? So notice for the x, there's no point at x equal 2 right here, right? And for the y, there is no point right here at 1, nothing. Okay? So you can see that the function only exists in just very specific places. It doesn't exist everywhere like this continuous one, right? So those functions we call discrete. Okay, so we're going to dig into those kinds of functions today. Okay. So a discrete function, again, not connected by a line or curve. What does that mean in practice? Well, for example, if we're talking about the number of students in a class can have 25.67 students, right? It's either got 25 students or 26 students, nothing in between, okay? So same for, you often hear that the number of children in an average family is 2.3. Obviously, the family doesn't have 2.3 children. They either have 2 children or 3 children, okay? So there's no 0.2 or 0.3 kid running around, okay? So it should be obvious by now that discrete data is not continuous data, okay? So here, it's not continuous. The dots are not connected, okay? So that's the kind of graph we're talking about. So the discrete graph I showed you is one example of a discrete function. Here are 3 more examples, okay? So here in this table, okay, the x's are on the top row. See this? These are all the x's, and notice I color-coded the x's to be green. And y is the second row. Okay, notice I've coordinated that color to be purple. Okay, so this is how you might encounter a discrete function in the table format. Okay, another format that you might encounter is called a mapping. And what that is it's 2 columns, right? The x's are on the left. Notice that the x's seem to always come first, right? And then the y's are on the second column on the right. Okay, but what makes this how it communicates to you that this x goes with that y is the way they draw the lines. Okay, so here, for example, you'll see that the 0 for x goes with the y for x. Notice, since none of these x's go to any different to 2 different y's, this is also a function. Okay, and then the last thing on this page, a discrete way of specifying a function, a discrete function, is an ordered pair, ordered pairs, a set of ordered pairs. So the set S is all these points, just like these are points, discrete, these are points, and now these are points. Notice, instead of separating the x's and the y's like it did with the table and the mapping, in an ordered pair, it's xy, xy, xy. So each of the points are organized in this way. Again, I've color coordinated the x's to be green, the y's to be purple. Okay? So let's keep going. The reason I wanted to introduce you to those kinds of function representations is we want to start talking about a little bit more about functions. Functions, as you know, have an input and an output. For example, here's a function f, right? The input goes in the parentheses, and that input is x, okay? And then after I calculate the function by plugging in the x, I get an output, and that output we typically say is y. How do I read this funky f parens x? We say f of x, okay? Function of x, f of x, and the result is y, okay? All right, so how do we do that? So for our first thing that we saw that was discrete, a discrete function, it was a graph, okay? So for this graph, I've labeled the x-axis, right? Goes on the horizontal side, and the y-axis, the vertical axis, okay? Notice, here's our definition of a function, f of x. I put in the x's in the parens, and I get some kind of y, okay? So let's take a look at this. Here, the ticks are each tick here is 1. The labels go by 2's, but the ticks are 1. So for x on the x-axis, x equal 1, what's the y? What's the output for if I input a 1 for x? Well, according to this, the y is 2. So for x equal 1, the y is 2. So for x in the parens, x equal 1, the answer, the output, is 2. What about when x is 3? Well, 1, 2, 3 for x. What's the output? 1, 2, 3, 4 for y. So for f of 3, we get the answer of 4. What about f of 5? What happens to the if I put inside the function, if I input a 5 where it says x? Here's x equal 5. What is the y? 1, 2, 3, 4, 5, 6. So when I input of x equal 5 into the function outputs a 6. So if I input a 5 inside of the parens in the function, the output is 6. I'm going to pause here so that you can practice on your own and tell me, if I input a 7, what is the output? And if I input a 9, what is the output y? Okay, I'll pause while you figure that out. Okay, we're back. And here, f of 7, if I plug in a 7, I get 1, 2, 3, 4, I get 5 for y. And if I input a 9, there's 2, 4, 6, 8, and a 9, what y do I get? 1, 2, 3. Okay, so hopefully you got that as well. So that's the function notation, this kind of notation for this discrete graph. Okay, let's take a look at those three others, the table, the mapping, and the ordered pair. Okay, so what outputs do we get when we put in these inputs, the x's that are green, right? So for example, in this table, notice that the x again are on top and the y's are on the bottom. Okay, so if I input into the function a -6, f of -6, when the function adds on your input of -6, what does it output? Well, a 4. Okay, so f of -6 is a 4. What about if I input a -4? Well, if I input a -4, I get a 6. And what about if I input a -2? Well, f of -2 is 8. Okay, so once again, I'm going to pause to give you a chance to practice identifying the function notation for a table. Okay, we're back. So if I input a 0 for x, f of 0 is 10. The y is 10, the output. Okay, if I input a 4, the output is 14. So f of 4 is 14. Okay, so that's in the case of a table. Okay, what about in our case of the mapping? Okay, notice that if I input a 10 for x, what is the 10 paired up with? Well, it's paired with the y of 10. So the answer, the output, is 10. What about if I input 5? Well, f of 5 is matched to a 20 as the output. So there's 20. What about f of 0? Well, if I put 0 in where the parentheses says put the x in, f of 0 is 0. It yields an output of 0. Okay? All right, so I'm going to pause yet once again to let you figure out what is f of 6 and what is f of 9. Okay, we're back, and here we go. If I start with x as 6, it's paired up with an 18. See, f of 6 is 18. Okay, and then if I input a 9 for x, f of 9 is outputting 812. Okay, so that's our case for the mapping. Lastly, what about for the ordered pairs? Okay, well, I see here that if I put in an x of -2, it is paired with an output of 1. So f of -2 is 1. Okay, so just to remind you, f of -2 is 1. All right. What about f of -1? What's it paired with? Well, the y that it's paired with is 2. Okay? So f of -1 is 2. And f of 0, when I put in 0 for x, the function outputs a 3. Okay? So now I'm going to pause once again so that you can figure out what do I get as an output when I input a 1 and what is f of 3. Okay, we're back. And the answers are f of 1 is 4. So if I input a 1, I get output a 4. And if I input a 3 into the function, it outputs a 6. And so that's how we handle ordered pairs. Okay?